Next, we move on to the sampling distribution of sample variance. For sample mean, both the situations are done. Now we will look at the sample variance. And the result says that if you have a random sample of size n from a normal population and you define the sample variance in this way, so I have already told you why there is n minus 1 over here, then sample mean and sample variance would be independent. Also, n minus 1 times s square by sigma square, that is over here, this is going to follow chi square with n minus 1 degrees of freedom. So the same thing that we used in the last proof, but since this basically is talking about the sampling distribution of the sample variance, that is s square. So that is why I have kept it separately in this theorem. So you see that the first part, that is sample mean and sample variance, are independent. This proof basically requires a lot of rigorous statistics, and this can be proved using the Basu's theorem. But here we will not be focusing on that. You can just understand it is that it is a result where that sample mean and sample variance would be independent. Now with this background, we are going to find out the sampling distribution of this over here. N minus 1 times s square, if you see, if you take n minus 1 to the left hand side, n minus 1 times s square would be same as summation xi minus x bar whole square divided by sigma square. Okay, so instead of writing this, we can use this also in the numerator. So let us try to prove this. So this is your theorem 6. Okay, and our interest is in proving n minus 1 times s square by sigma square. This follows chi square with n minus 1 degrees of freedom. Okay. Note that if we have to prove any such thing, then you can keep in mind that we have a very useful technique of MGF, which can help us in getting the distribution of the transformed random variable. So in this case, MGF, suppose if we have to find, so if I can prove that the MGF of this, suppose I denote it by U, if I can show that MGF of this random variable at t is 1 minus 2t to the power minus n minus 1 by 2, then this would be your chi square distribution basically with n minus 1 degrees of freedom. Because in general, if you have a chi square distribution, okay, so for a chi square distribution with n degrees of freedom, the MGF is 1 minus 2t to the power minus n by 2. Okay, so if it is chi square n minus 1, so the change is coming in n minus 1. So where t is less than 1 by 2. Okay, so here also the same thing would be applicable. So let us try to see. Now chi square n minus 1. So if we need something like this, we might have to go with this idea that if I have some with chi square, some random variable follows chi square with n degrees of freedom, and I can also find another random variable which is chi square with 1 degrees of freedom, then I could possibly get chi square with n minus 1 degrees of freedom. So we would begin with this idea and start to define the random variable over here. That is, so let us first of all, so we will define W over here as summation xi minus mu by sigma whole square I1 to n, because here we have summation xi minus x bar, because this is what? This is summation xi minus x bar whole square in the numerator, right? So instead of that we are working with, and we can divide it by sigma square also. So this is basically somewhat in this fashion only, with just the replacement that instead of sample mean we are working with the population mean over here. Now if you look at this, here we can add and subtract the sample mean. It won't make any difference. So xi minus x bar plus x bar minus mu whole divided by sigma whole square. Okay, so I can take this term and expand it. So let us see, what do you get from here? Light summation. If you focus on this part, this is what? Xi minus x bar by sigma whole square. Okay, plus x bar minus mu by sigma whole square plus twice of x bar minus mu by sigma into the other term, that is xi minus x bar. Okay, if you take the summation inside, what do you get here? Summation xi minus x bar by sigma whole square plus, it will be this, with second term would be n times of this. Okay, plus twice x bar minus mu by sigma. And when you take summation inside, what happens to this term? Let us see. Summation xi minus x bar. What is this? If you take the summation inside, summation xi minus n times of x bar what is summation xi? Summation xi is also nx bar only, right? So this quantity over here gets 0. So the third term basically is 0. Okay, what is happening in these two terms? Let us see. This is basically your u, right? Summation xi minus x bar by sigma whole square. This is our interest of random variable. And what do you see from here, this side? If we denote this by v, okay, so v is basically here what we have done. If x bar, we know that if x bar follows normal with mean mu and variance sigma square by n. Okay, and I can standardize it, x bar minus mu sigma by root n. This would follow normal with mean 0 and 1, And if I take the square of this random variable, this is going to follow chi square with 1 degrees of freedom, because there is only, we are talking only about x bar over here. So here again it will be following chi square with 1 degree of freedom. And this is what is your v, because v is same thing. N is in the numerator, x bar minus mu by sigma whole square. So v over here that you have, v follows chi square with 1 degrees of freedom. Okay. And if you look at this initial point that we had here, W, what is W? What is the distribution of W? From the same logic that if xi's are following normal, right? Xi's are coming from the normal population. So this standardization would be standard normal variate. And if I square it up, we have just now seen, squaring it up will give me chi square, 1 for each of them. And if I add it up, it will follow chi square with n degrees of freedom. Okay. So on the right hand side, you have W, which is U plus V. Okay. And we have seen that W is following chi square with n degrees of freedom. And this is following chi square with 1 degrees of freedom. So if you use the MGF technique over here, moment generating function of W at t would be expected value of e raised to the power t W. What is W? Substitute the value of W. U plus V. This is what? This is expected value of e raised to the power tu into expected value of e raised to the power t v. Okay, this is basically the moment generating function of u at t, and this is the moment generating function of random variable v at t. So for W we know it follows chi square distribution with n degrees of freedom. So its MGF would be 1 minus 2t to the power minus n by 2, right? And here V is following chi square with 1 degrees of freedom. So its MGF will be 1 minus 2t to the power minus 1 by 2. So what will be the MGF of u? It would simply be 1 minus 2t minus n minus 1 by 2. Okay, which shows that u follows chi square with n minus 1 degrees of freedom. Okay. So u is what? U is basically n minus 1 times n minus 1 times s square by sigma square follows chi-square distribution with n minus 1 degrees of freedom. So whenever we are talking about sample mean, basically the sampling distribution of sample mean, then we come across two distributions, that is your normal distribution or standard normal and the t distribution. Whereas whenever you are talking about the sample variance, you will come across your chi-square distribution with these many degrees of freedom. Okay, so this is the entire proof for it. Let us consider an example over here. In a bolts manufacturing process, the diameter of a certain type of bolts is normally distributed with mean of 8 cm and variance of 1.23. So mean is given to you, mu and sigma square is given to you, and n is given to you as 10. Your question is that find the probability that the sample variance, that is s square, is going to exceed 2. So you have to find the probability that sample variance is greater than 2. So we can note down the details for your fifth example. So sigma square is basically 1.23 and n is 10. You have to find the probability that sample variance is greater than 2. Again, we can simply use the result. So since we have this result over here, we can write it in the same form. N minus 1 times, that is 9 times of s square divided by sigma square, that is 1.23. This would be greater than equal to n minus 1 again over here. So n minus 1 would be 9. 9 divided by 1.23 into 2. So here this would be basically chi-square random variable with the 9 degrees of freedom. And here if we solve this, this would come out as 9 to the 18 divided by this comes around 14 point. Which when you, so this basically is same as 1 minus of this probability. That chi-square 9 is less than 14.63. Okay, so this value from chi-square table, this probability, you can see that it is you go to this 9 degrees of freedom, and there if you search for this particular value, you will find that it corresponds to 0.900. So basically what the probability final answer is 0.10. One more thing that you can note over here is, here it is following chi-square n minus 1 degrees of freedom when you have summation. This is what? Summation xi minus x bar whole square by sigma square. right? However, when you have summation xi, that is w is what? The only difference is coming in this, right? Instead of mu, you have sample mean over there, and here it is following chi-square with n degrees of freedom, and there it is following chi-square with n minus 1 degree of freedom. So basically, when you are estimating mu by sample mean, 1 degree of freedom is lost in that case. Okay. So we now move on to the sampling distribution of sample proportion. So we have seen for sample mean and sample variance, which mean and variance, these are the summary measures for your numerical variables, and when we talk about proportion, we can deal with the categorical variables. So here the sample proportion is basically defined as x over n. So where x is the number of individuals in the sample who have that characteristic, and n is the number of individuals. Okay, so proportion we calculate in this way only. And if you note that here this x over here, this is basically your binomial random variable, because when it is a binomial random variable, what we do over here, in that case, the random variable x is the number of success in n independent Bernoulli trials. So here also, if you see, x is the number of individuals in the sample with the given characteristic. So whichever individual that we can consider a success as the situation where the individual would be having that particular characteristic. So the total number of individuals can be divided into two categories. Either they will have that characteristic or they will not have that characteristic. So basically, getting a person who has that particular trait will be your success, otherwise it will be a failure, and we are looking at n individuals. Okay, and all these xi's over here will be independent, because outcome of one trial is not affecting the outcome of the other one. If one person can have that characteristic, that does not mean that the other person will not have that characteristic. So this is basically, x is your binomial random variable in this case. So if we know that binomial random variable has two parameters, n and p, and x is basically the number of success in n independent Bernoulli trials, and its PMF is in this way, where x takes value between 0 and 1 to n. Because the number of success can even be 0, that means that no person is there who has that characteristic. There is a single individual who has that characteristic, and likewise we can at max have n individuals who have that characteristic in a population of size n. And in this case, we also know that its mean is np and variance is npq, that is 1 minus p. Now, if you know that x is following binomial distribution, then it becomes very easy to deal with the sample proportion, because sample proportion, which is p hat, is nothing but x by n. Okay, so if I have to find the mean of p hat, so instead of p hat we can write x by n. Again, we know that n is a constant, it can go out, 1 over n expectation of x. Now since x is following binomial distribution, expectation of x will be np, and n will cancel out, you will have p only. So expectation of p hat is p, so it is again having that characteristic unbiasedness, because this is a sample proportion and you are getting a population proportion. Okay, so you have this, that it is an unbiased estimator. If you can recall from the very first theorem, we had a similar result for expectation of sample mean, that is expectation of x bar came out as mu, that is population mean, and likewise we had expectation of sample variance also as population variance, that is expectation of s square was sigma square. Here also you have the same condition result. Now if you calculate the variance of p hat, then variance of p hat is nothing but x by n. N, if you take it outside, it will be n square, because we are dealing with variance over here, and variance of x for the binomial random variable, it will be npq. So 1 n will cancel out, it will be pq by n, or you can say p into 1 minus p by n. So obviously the standard error, that is nothing but the standard deviation of the sample statistic. So it is a square root of this. So it will be root p into 1 minus p by n. Now with this background, we can finalize this theorem over here, which states that if you have a random variable following binomial distribution with parameters n and p hat is given to you, that is the sample proportion is x by n, then if you have a very large sample size, that is when n is for large sample size, p hat is approximately normally distributed with mean as p and variance would be p into 1 minus p by n. So p, you can see that we just now found here that expectation is this, variance is this, but here based upon this we cannot simply say that it is going to follow normal distribution. For this we need to prove how the normality is coming in picture. So let us prove this. So this is the last theorem of this week, which is the sampling distribution of the sample proportion. So here it says that if x is following binomial with parameters n and p, then we know that by the relation between binomial and Bernoulli. So binomial is basically the generalization of binomial is basically the generalization of Bernoulli, right? Because Bernoulli says that number of success in a single trial, Bernoulli trial, whereas in binomial you have number of success in n independent Bernoulli trials. So we are just generalizing it. So you can think of x basically as summation xi's where each xi follows binomial with parameter 1 p, which is same as saying it is following Bernoulli with parameter p. Okay, if this is the case, then we know that x would follow binomial, right? And in this case, what will be your p hat? P hat, we have already said that p hat is x by n. Now instead of x, we can write summation xi's. This is what? This is the sample mean basically. Fine. Also, since it is binomial, if we look at the variance of this quantity, variance of xi's, it would be just simply be p into 1 minus p. Because for Bernoulli, the variance is just PQ. Fine, which is a finite quantity. So if you consider that this is p n hat is same as x n bar, so you add this suffix n over here, then you can standardize it, because here you can apply the central limit theorem, p n hat minus p, because p n hat we know that x bar minus mu, right? We have this result that x bar minus mu sigma by root n would follow normal with parameters 0 and 1. Normal with mean 0 and variance 1. So same thing if you apply. So instead of x bar, we can write p n hat minus mean of this x bar. So mean of p hat, we have seen that it is p. Say expectation of p hat is same as p. Now you divide by its corresponding standard deviation by root n. So this would be p times 1 minus p divided by n. So this basically would follow it will be approximately normally distributed, right? Because now again we can use the central limit theorem to show that it follows normal distribution with mean 0 and variance 1. That is why we say that as n approaches infinity, then this distribution would approach to your standard normal variate. Okay. Now for this result to hold true, we have two conditions. That in general it is mentioned that np should also be greater than 10 and n1 minus p, this also should be greater than 10. In some places you will find that this instead of 10 they consider the criteria as 5. So np should be greater than 5 and n into 1 minus p has to be greater than 5. If these two conditions are satisfied, then you can use this approximation. Okay. Now the last example. Suppose that in a city, the proportion of individuals who have watched a movie in the past week is 0.45. So you are given that the sample proportion is this. So now we will come to the sixth example. Here, suppose in a city, the proportion of individuals who have watched a movie in the past week is 0.45, and in a survey involving a group of 250 people from the town, you have to find what is the probability that the proportion of individuals who have watched a movie in the past week is less than 0.35. So n is 250. You have to find probability that this sample proportion, that is p hat, is less than 0.35 and your population proportion given to you is 0.45. So let us solve this. So p is given to you as 0.45. N to you is 250. We have to find the probability that p hat we have to find the probability that the proportion of individuals who have watched a movie in the past week is less than 0.35. So again you can same way subtract the population proportion, divide by the standard error. So the standard error in this case, here we know that standard error of p hat it would be this p into 1 minus p by n. So let us subtract p hat minus 0.45 divided by the standard error. So standard error is basically 0.45 into 0.55 divided by 250, square root of that whole thing. So again find this value. So this is some standard error over here, and this is less than so 0.45. So this is basically minus over here, because 0.35 minus 0.45 divided by the standard error that you will find over here. Okay, so the standard error comes out as suppose 0. So we have your sixth example. So P is given to you as 0.45 and N is given to you as 250. Okay, the standard error would be basically be square root of P into 1 minus P by N, right? So which is basically 0.45 into 1 minus 0.45 divided by 250. So this comes out, if you solve it, you will get 0.0315. And finally, you have to find the probability that P hat is less than 0.35. So this is the probability that P hat minus, you will subtract P, that is 0.45, which is given to you, divided by the standard error. So which is 0.0315. It will be less than 0.35. You will subtract the P again, that is 0.45. You will divide by the standard error, that is 0.0315. Finally, so this side will become your standard normal variate, and this one would be minus, because minus is coming, and it would be 0.317. You can check these values, and when you look at the standard normal table, this comes out approximately 0.3756. So you have used the CLT and this approximation because here NP and N1 minus P both are greater than 10. So that criteria is satisfied. That is why you were able to apply this approximation, that in the binomial setup you are taking this central limit theorem, and by standardizing it you are using the standard normal table over here. Okay, you can either look at the tables or you can just check using some software, and you can also get these values. So this was all about your fourth week, that is on sampling distribution. So here we primarily focused on single sample problems. So basically from a given population we are taking only a single sample, and then we were understanding what will be the sampling distribution of the sample mean, sample variance and sample proportion.